Hi everyone, so welcome again to the seminar. Today it's my pleasure to introduce Pat Scott from UQ. So Pat Scott originally did his honours at Mount Stromlo Observatory in Canberra before moving to do a PhD in Stockholm and then holding positions in McGill and also a lectureship in Imperial. But he's now a future fellow at UQ as of 2019. And one of Pat Scott's main projects is what he's going to be talking to us today about, which is this very large Bayesian inference tool called GAMBIT for doing lots of stuff in astroparticle and high energy physics. And it's really wonderful to have Pat Scott here to tell us about this. So thanks again, Pat, and take it away.
Thanks a lot, Kieran. I guess thank you for the very nice introduction. I will just point out that GAMBIT's not only Bayesian inference, it'll also do frequentist inference for you as well. So if you're a particle experimentalist who doesn't like Bayesian statistics, don't despair. So what I'm going to do is basically tell you a little bit about what's new in GAMBIT. So we had a new version come out only a few months ago, version 2. And the big thing there is that you can now basically do global fits directly from a Lagrangian. So you can give GAMBIT a Lagrangian and it'll generate a whole bunch of code that will work out cross sections and things like that for you. And then you can run a global fit from there. So I'll tell you how that works. And I'll also talk a bit about some related tools that we've got coming out and some latest physics results on effective field theories for dark matter. So, first I'll give you a little bit of a background, introduction to GAMBIT and what the problem is we're trying to solve. So how do we actually go about identifying which parameter values in a given theory for new physics are good ones and which ones are bad, and which theories overall are good and which ones are bad? Obviously, we want to compare with the results from experiment. There are lots of different experiments in lots of different areas, collider searches, dark matter searches, flavor physics, all these different things, cosmology. What we really want to do is to actually combine the results from all of the different searches from all of these different areas in such a way that we have a full picture of how constrained the different parameters are of the different theories. So the simplest way that you can imagine doing that, can you all see my cursor okay?
Yeah.
Cool. The simplest way you can imagine doing that is basically just getting something like 95% confidence exclusion regions from each experiment, and you say, okay, this area is excluded by this experiment, whatever green experiment, this thing's excluded by red experiment, and then saying basically that everything that is excluded by something, by one experiment or more, is ruled out, and everything that has not been excluded by an experiment, so the stuff in white, is okay. Now, this works as a kind of a back of the envelope thing, but it throws out a lot of information because you've given up on the fact that you actually know that things over here are a lot more excluded than things over here, and that things close to the 95% confidence region are actually a little bit excluded as well, that they're worse fits than stuff right in the middle here. And you've also given up on the fact that, say, in these overlapping regions, you've got multiple experiments that have ruled out this theory. So what you really want to do is actually combine the likelihood functions for these and come up with a combined likelihood function that you can then draw your exclusion contour from. So here I've got the same 4 functions, but where the likelihood functions have been multiplied and then drawing a 95% exclusion curve based on that combined likelihood function. You can see that it's qualitatively different to this curve that you get just from overlaying 95% regions. I should say also, please interrupt and ask questions. Don't wait till the end. Quite happy to have discussion in the middle. So what if you've got lots of free theory parameters? I mean, this sort of setup that I've shown you here works really nicely when you've only got 2 parameters. I can just draw it all in a plane. If you've got a lot of additional free parameters, you really need to start doing a detailed statistical comparison and careful sampling. So you need to choose a statistical framework, so either Bayesian or frequentist statistics, and then sample the parameter space carefully according to the requirements of that particular framework. So if you're doing Bayesian statistics, you basically need to use a sampler that's more or less an integrator. Whereas if you're doing frequentist statistics, you actually want to look at something that's designed more as an optimizer, and that's basically to find the best fit as opposed to basically finding the regions that give you the highest posterior probability density. Okay, so that's good. You can set up a framework to do this for any given theory without too much bother. But if you want to do it all over again for many different theories, then it's a fair bit of work, because you need to basically design the whole framework differently in many of these cases. So you need to include different results from different searches. You need to have different theory calculations, and then you need to hook all of those up to the statistical sampling machinery. So this is why we came up with Gambit. The idea here is basically to have an overarching code framework that will allow you to do global fits of more or less any model, and to pick and choose the different experimental likelihoods that will be applied to the different theories according to which ones are actually valid for that particular theory. So it basically allows you to do a plug and play sort of analysis of different physics scenarios, where you can introduce new likelihood packages easily, new models easily, also new sampling algorithms, things like this. So it comes with a big database of models. It comes with a big database of experimental data and corresponding likelihood functions, has a bunch of different statistical options, and it's fully open source, and it's basically set up so that it's really optimized for doing fast scans. So it's got a fast LHC likelihood calculator, and it's heavily parallelized. So depending on what theory you're working on, you can do it on your laptop, or you can go to the world's biggest supercomputers and run for many days there. Gambit's actually three different things. It's this code, but it's also a collaboration of over 70 people now, from both theory and experiment, and also astroparticle and particle physics. And it's also basically a program of physics analyses that we're doing using the code. So by this time, we've put out about 20 papers using Gambit, and more than half of those have been physics analyses as opposed to like manual papers. So it's broken down into different modules that, for the most part, are arranged around the different physics themes. So there's a collider physics module called ColliderBit. DarkBit takes care of dark matter things. FlaveBit does flavor physics. SpecBit basically takes care of spectrum generation. DecayBit does the decay rates of new particles and also standard model particles. PrecisionBit takes care of precision tests of new physics, so typically things based on very rare processes. There's a relatively new couple of bits in the last couple of years, NeutrinoBit and CosmoBit, so neutrino physics and cosmology. And then there are two statistics modules. So one is ScannerBit, which is the main one that basically drives the sampling. So this contains interfaces to all of the different sampling codes, and takes care of the priors and stuff like that. And then there's ObjectivesBit, which is basically a container for a bunch of test functions. So each of the module functions consists of, each of the modules consists of a number of smaller module functions, and the individual module functions basically calculate a single physical quantity or a single statistical quantity. And they're the real building blocks of Gambit. So you can declare these things to have dependencies on each other. So if I have a module function that, say, calculates a dark matter flux, it might have a dependency on the dark matter mass and also on the dark matter annihilation or decay branching fractions. And then those things might have dependencies on other things, and so on and so forth, until you get back to the actual original values of the parameters in the theory. It also has a hierarchical model database. So every model in Gambit goes into this database, and it's defined by the identities of its free parameters and also its relationship to other models. And the sorts of relationships I'm talking about here are actually inheritance relationships. So it means that you can have child models that descend from parent models, which means that they're actually subspaces of the parent model. So you define a translation function that allows you to basically up-translate any point in the child model parameter space to a point in the parent model parameter space. So what that means is that once you get to sufficiently complicated ancestries of different models like we have in one of the arms of SUSY that we've got in GAMBIT that I've shown down here, you really can get all of these translations to happen automatically and basically design all of your individual physics calculations to work with some of the higher models and then just have them automatically work with all of the lower models. Even though you might do a scan of the lower model in whatever sort of not obviously related parameterization down here, it'll all be up translated automatically and the correct model will be used for the particular theory calculation you've written. So this is nice because it means that you can reuse stuff very easily, but it also means that you track the model dependence of the different calculations and you really ensure that you're not using anything that is model dependent and not able to be used for the particular model that you're looking at. So when you actually fire up GAMBIT and say, I'm going to do a scan of model X, what you need to do is to tell it what model you're going to scan and what the experiments are that you want to use to constrain that model. Once you do that, GAMBIT basically goes off and looks at this big database it's got of all the different module functions, turns off the ones that are not compatible with the model that you said you're going to scan, and then it goes and looks for functions that are able to calculate the things that you said you want to use to constrain your theory. So the values of the experimental observables and the likelihoods that you want to use in your fit. So in this particular example I've got here, this is a scan of some Wilson coefficients for flavor physics, and this is just using two observables from flavor physics, B2S gamma and B2LL. And so what I've put in the input file here is just these two, and basically GAMBIT works backwards to find what it needs to plug into these functions in order to be able to compute them at the end of the day. So it goes and says, okay, so my user said that I need to use B2S gamma. What do I have that can compute B2S gamma? Okay, I find this function B2S gamma LL. What does it need? It needs this B2S gamma, and then so on and so forth. So it hooks all of these things together into this graph, and eventually it works all the way back to the actual parameters of the theory. So these are the beginning of the whole information chain. So we have the Wilson coefficient parameters, we have the standard model parameters in SLHA2 parameterization, and then we also have the standard model Higgs sector parameters. So at this point, you've got this graph. It's what's known as a directed acyclic graph, which basically means that the information flows in a specific direction. So these arrows show the direction of information flow. And then the acyclic bit means that there are no closed loops. So that means that you can basically solve this graph and work out an ordering in which to run each of these functions such that all of the dependencies get satisfied. So GAMBIT does that, and then it basically starts pumping parameter values through this graph. So you can see from this that I can automatically adapt to whatever model or whatever combination of constraints that you want to apply to your model. So like I said, we've used this so far for studying a whole bunch of different theories. We've put out a number of papers. Sorry, I'm just trying to work out timing. Okay. So we've looked at a number of different versions of supersymmetry. So there's gut scale SUSY. There's also weak scale SUSY, this so-called 7-parameter MSSM. And what's effectively an electroweak effective field theory, various Higgs portal models, axions and ALPS, different neutrinos. So we have the best limit on the mass of the lightest neutrino so far, for example. And the one that I'm going to talk a bit more about today is this dark matter effective field theory fit. that came out earlier this year. So this is the basic outline of the rest of the talk. So first I'll tell you about the new stuff that allows you to go directly from the Lagrangian. This is what we call GUM, or the GAMBIT Universal Model Machine. Then I'll talk about the dark matter EFT results, and then I'll, depending on how time is going, say something very briefly about this thing called ColliderBit Solo. So GAMBIT version 1, the way it worked when it came out is basically that it contained a bunch of code for computing observables in different theories. So here I'm just showing sigma for cross sections, but you can sort of think of this as a proxy for basically like all observable quantities. And it contains basically a generic way to go from those to likelihood functions for many different experiments, and then to do the sampling and to generate plots for many different models. Now, the difficulty here is that the traditional way of setting this up in Gambit is that you basically have to code the models and these module functions that would do the theory calculations by hand. You could make use of external codes. You could hook up to basically any external code as what we call the backend. And a lot of the theory calculations were based on doing that. Not all of them. Some of them were implemented natively in Gambit. But it meant that there was, still significant overhead in implementing a new model in Gambit. So that meant that, in general, you had to, if you were going to look at a completely new model that was unrelated to any of the existing models via the model hierarchy, you needed to introduce new code for actually computing cross sections or other observables. But there's a whole ecosystem of theory tools that are really based on going from the Lagrangian to matrix elements and generating code for theory calculations of observables. So the first version of Gambit was really doing the bottom end of this calculation, and pretty much nothing existed for doing this in a generic way before. And part of the reason we went for that was that tools did exist for doing the top end of the calculation. But in the first version of Gambit, we decided, to focus on getting the whole tool chain working nicely for the bottom end. And the plan was always to come back and then hook up all of the theory tools further up the chain in version 2. So that's what we did with this Gambit Universal Model Machine. So it becomes clear from this that you basically need a pre-Gambit step that uses a lot of these existing theory tools to write a bunch of Gambit code based on the Lagrangian. So to call all of these theory tools and get the code outputs of those, and then also automatically write a bunch of code for Gambit itself. So this is how the whole information flow basically works within GUM, the Gambit Universal Model Machine. So you run it before you run Gambit, and you give it either a fine rules and or a Sarah model file. So from the Lagrangian, you basically you're feeding the Lagrangian basically the fine rules and or Sarah. GUM works out how to write the necessary code to put the model into Gambit, and then it runs fine rules and or Sarah, and gets the outputs of those, feeds them to the next level of tools. So you can use MadGraph then to generate matrix elements, CalCep to generate code to give you decays and cross sections, Spheno to also give you decays, but also spectrum generation code, and Vivacious to give you code to compute vacuum stability. We then take the matrix elements that come out of MadGraph, put them into Pythia, and hook up that new version of Pythia along with a bunch of other code generated by GUM to ColliderBit. So that makes ColliderBit support the new model. We take the output of CalCep, feed it into micromegas, and we also take those outputs and feed them into DecayBit so that we have the new decays. We hook the new version of micromegas up to dark bit, so this gives us a whole bunch of new dark matter observables that we can calculate for that particular theory. And via DecayBit, we actually also get the ability to use dark SUSY to compute a whole lot of stuff for this new theory. So this is sort of somewhat indirect because DarkBit will use pieces from dark SUSY along with existing contents of the decay table to compute relic densities and things like that. So it means that we then have the ability to use both micromegas and dark SUSY with generic models. Micromegas is set up for this natively, dark SUSY is not. So this, in some sense, is like an extension of the capabilities of dark SUSY. We take the outputs of Spheno. So the decay widths, also put them into DecayBit. You can basically choose whether to use the CalCap or Spheno ones. And the spectrum generation code goes into SpecBit, and that's used together with Vivacious to give you the vacuum stability and also to actually calculate the masses of the particles involved. So if you actually want to go out and run GUM, this is basically the entirety of the task in front of you. So first of all, you need to write down your Lagrangian in a fine rules or a Sarah file. So you basically need to write your own fine rules or Sarah model file and put in any corresponding constraints or other things like that you want to use. You then write a configuration file for GUM. So this is an input file for GUM where you tell it basically how to treat the fine rules model file and then what things you want to generate inside Gambit. So you say, okay, I'm going to use fine rules. I'm going to give my model this particular name. So this is actually the example from the GUM paper. It's a Majorana dark matter simplified model. So it's so this Majorana dark matter here chi and a scalar mediator y that has some Yukawa type couplings to standard model fermions. So I basically specify what the Lagrangian is of this model. So it's this dark matter Lagrangian plus the standard model Lagrangian. And I add some restriction files here for use in fine rules. I specify what the dark matter candidate actually is in this fine rules file. And then I'll say, okay, which things do I actually want to generate output code for? So in this case, I'm not generating pithier outputs. So I'm not actually creating new matrix elements and putting them into ColliderBit, but I am generating output with CalCap and micromegas. So once you've done that, you run GUM. So it's as simple as running this command. And then GUM will basically go through and run fine rules and or Sarah and all of these other tools and generate a bunch of code and put it there ready for you to put into Gambit. So it does all of the modification of Gambit. It keeps track of what it's done so that you can reverse it as you might expect. And then you need to go and build Gambit and also any new versions of the external codes that is generated. So you reconfigure Gambit using CMake and then make the relevant backend. So in this case, we're making micromegas specialized to this particular model, making CalCap. We're making GAM-like, which is a gamma ray likelihood backend that we made, and then DD-Calc, which is a direct detection backend likelihood that we also made, and then building Gambit. So this J is just saying build Gambit in parallel because sometimes it takes a while. So then you've got a version of Gambit that supports this new model, and it's just a matter of actually writing a Gambit input file for the global fit of that model that you want to scan. So this is not a full Gambit input file, but it's an excerpt of the kind of some of the most relevant things. So you specify the model that you want to scan, and then you specify ranges and priors on each of its parameters. So here I'm saying that I want to scan dark matter masses between 45 GeV and 10 TeV. I'm going to apply a log prior to those. Then yeah, got ranges for the three other parameters in this theory. And then you say what things you'd actually like to use to constrain the theory. So in this example, I'm saying, okay, I want to use the log likelihood from the dark matter relic density to constrain the theory. If you go and look at the example file, you'll see a whole bunch of other observables listed there as things to include in the fit. So then step 6 is basically just to run Gambit and do your global fit. So for this particular example model, we've got 4 parameters. So this plot is the preferred parameter space of this theory in terms of the mass of the dark matter particle and the mass of the mediator. So here we're looking at the profile likelihood. So the 2 other parameters, the dark matter coupling and the mediator coupling, these have been profiled out. So that means that for each combination of mass here, we've selected the couplings that give the best possible fit to all of the data. This isn't done in the process of the fit. It's done just in the process of generating the plot. So we have samples for all sorts of different values of these couplings. So what you can see here is basically that in this particular simple model, as long as you're above this red line where the dark matter can annihilate to the mediator directly, then it's very easy to satisfy the Rayleigh density and all of the other constraints, and you're pretty good. Below that, you can see that there's a preferred reasonable parameter space where you can have annihilation on resonance, where the dark matter is annihilating its downward fermions via a resonance with the mediator. So this fit includes the Rayleigh density likelihood as an upper bound. So we allow models that have a subdominant dark matter, where the chi is a subdominant component of dark matter. It's got constraints from xenon 1-ton and lux, also the dwarf spheroidal galaxy constraints from Fermi-late gamma rays. And this particular scan you can actually do on a laptop. So this took 11 hours on a 4-core laptop, and it came out with about 300,000 samples of different parameter values before it was converged. So one thing you'll notice is that this example doesn't include the collider physics. That's basically because if you want to do explicit Monte Carlo of this theory, it's going to take an awful lot longer than that. So this is an example where instead you generate, or instead you only turn on the LHC likelihood. So this is a 1D scan of the same model where we're just varying the mediator mass. So this has a fixed dark matter mass and fixed couplings. So you can see in this particular slice, there's an area of low mediator mass that's fairly strongly ruled out by the LHC. If you vary the other parameters, you can find cases where low mediator mass is allowed, right? Like over here. So in this example, we've only got one Atlas search turned on. So this is the Atlas 2 leptons plus jets plus missing ET search. I think this was a 139 inverse femtobarn search. And every one of these points includes 12 million Monte Carlo events generated with Pythia. So I don't remember exactly how long this took, but it was multiple days. So that's the explicit route if you want to actually use Pythia directly for this particular model. Some models it'll be faster, some models it'll be slower.
Can I just ask quickly? I don't know if you mentioned it. How are you actually doing the scan? What algorithm is you using?
I didn't say it. It's using this package called Diver. So this is a differential evolution sampler. So it's an optimization algorithm that's designed to look for the best fit and then map basically the likelihood contours around that best fit. Does that give you sufficient information?
Yeah, yeah, sorry, yeah, thanks.
more?
I was on mute. Yeah, thanks.
No worries. Okay, so yeah, the next thing I was going to talk about was recent results for dark matter effective field theory. So we did a global fit of a particular dark matter effective field theory. So the general dark matter EFT, it's pretty, it's very high dimensional parameter space. So here you would write down all dark matter standard model effective interactions up to some mass dimension n, where sort of free to choose n, right? You might, start with something small, 5, 6, 7. In principle, it's possible to actually do that and do a full global fit of the general theory with GAMBIT, but that's a massive undertaking. So we decided to start by focusing on the 16-dimensional space of direct dark matter that interacts with standard model quarks and gluons. So this is the Lagrangian of the theory. The 16 parameters come from the dark matter mass, the scale of new physics. So we take a universal scale of new physics for all effective interactions. And then the Wilson coefficients of each of these effective operators, QA. So we've got 14 of them. So there's 4 dimension 6 operators between the dark matter and the quarks. So these are the vector, various vector and axial vector interactions. And then we have 10 dimension 7 interactions. So these are interactions between the dark matter and the gluons, and then these other ones between the dark matter and the quarks. So these are particularly interesting when it comes to the different dark matter observables, because different operators here have different dependencies on the momentum transfer and the relative velocity between the dark matter involved in nuclear scattering and in annihilation. So looking at nuclear scattering, for example, these ones in blue, these give you non-suppressed spin-independent signals. So you'll probably recognize the scalar interaction here. This is the standard one that people usually refer to as quote-unquote spin-independent scattering. But then there's also the vector interaction, and then there's this one with the gluons too. There are also other spin-independent interactions that are actually suppressed by some power of the momentum. So these ones, they're spin-dependent, unsuppressed interactions. So this one here, Q46, this is the standard quote-unquote spin-dependent interaction. There's another one here, a tensor interaction. And then all of these other ones here that aren't colored, they're ones that are spin-dependent and suppressed. So I said that we include this lambda, this scale of new physics, as an independent parameter. So, we actually scan over that and sample it independently of the Wilson coefficients. If you want to maintain unitarity in the dark matter annihilation cross section without going into some additional mechanism for actually explicitly reunitarizing the theory, then you need to have lambda greater than twice the dark matter mass. So that gives you some more or less automatic constraint on the parameter space. However, you also need to make sure that your EFT is actually valid at all of the experiments that you're using to constrain the theory. So the way we do this is that we actually look at the scale probed by each individual experiment for each point in parameter space. So we compare that scale to the value of lambda at that point in parameter space. So if lambda is bigger than the scale probed by that experiment, then fine. The EFT should be okay. We compute the experimental likelihood and we include it. If not, though, so if the EFT is not valid for that particular experiment, what we actually do is to set the log likelihood to 0, which is to say that the experiment can't constrain the theory there. So we basically say that it's not disfavored, so it's allowed. So we give it a perfect fit in that case. Now, you need to be careful in how you interpret that, right? Because you probably would be sensitive to the actual UV completion, but we're doing an EFT analysis, so we're not specifying a UV completion, so we can't actually give any sort of sensible comment on how strongly that particular experiment would constrain arbitrary UV completions. It gets particularly complicated with the LHC because the different searches are such that there's only some parts of the data that would be invalid, or some parts of the data where the EFT would be invalid. So what we actually do is to leave out events where the missing ET of the events would be bigger than lambda. So basically, depending on the value of lambda, we smoothly cut off the predicted spectrum of the theory at different missing ETs. So there's a degeneracy in most of the observables as you rescale lambda and the Wilson coefficients, right? I mean, you can see that here. But because we actually do this because we vary the scale of new physics and the Wilson coefficients independently, and we do this thing where we look at each of the scales probed by each experiment individually, we actually end up being able to exclude more than in the kind of naive approach where you basically just demand that the EFT has to be valid at all of the theory. Sorry, demand that the EFT has to be valid at all of the experiments that you're including. So there were a few other things that we did in this study that were kind of important innovations. We used DirectDM to actually do a full renormalization group evolution from the new physics scale down to low energies. So we did a full match into the non-relativistic EFT, and then down at the hadronic scale, then used DD-Calc to compare with these detailed likelihood functions for the latest direct detection experiments. Also including nuisance parameters for nuclear uncertainties and halo models. The LHC constraints were based all on monogen analyses. So there's the full run 2 data set, Atlas 139 inverse femtobarn analysis, which is the thing that did the main heavy lifting, and then also at the time, the best CMS one was a 36 inverse femtobarn analysis that we also included. We included the simplified likelihoods available from CMS and profile over the nuisance parameters there. So that meant that instead of having to choose an individual signal region, we could include all of the signal regions. And then also included a bunch of indirect detection. So we had a relic density calculation for Duck-Suzy. We automated the cross sections and the gamma ray spectra by GUM. We had CMB constraints on energy injection in the early universe from dark matter annihilation, included by CosmoBit. And then using this external capture code, Captain General, we also had constraints from high energy neutrinos using IceCube, also using the new-like backend, based on the capture of these different dark matter particles with different momentum dependencies to their scattering cross sections. And then, yeah, this is all driven by Gambit and using, again, this diver differential evolution sampler. So this is the general picture of how a lot of the constraints end up looking. Basically, at large values of the new physics scale, you have the effective field theory valid for all experiments, but they're mostly insensitive at that sort of scale, and the constraints are mostly driven by needing to fit the Rayleigh density. At intermediate values, you basically have this just high enough to keep the LHC constraints valid, and you have strong constraints from the LHC. Whereas once you get lambda low enough, the LHC constraints become invalid, and you actually have a fairly large viable parameter space. So there are a couple of key results that came out of this. One of the interesting things was to look at the area at low dark matter mass. So for dark matter masses below 100 GeV, you can get viable parameter space if these two conditions hold. So either the dark matter is very subdominant, so you skip out of the direct and indirect detection constraints that way, or it has CP violating interactions, which basically mean that the scattering cross section at direct detection is suppressed. And in addition to that, you need the scale of new physics to be sufficiently low that the EFT breaks down at the LHC. So what this means is that in our likelihood, the LHC doesn't play a role. So we say, okay, it's effectively a perfect fit to the LHC because we don't know how the LHC, it can't really say anything. But that does mean that in the particular, UV completion that is really behind this EFT, the LHC would very likely be sensitive to the mediator itself. So this actually tells you that this area of parameter space is valid, but there's more to do, right? There's significant model building to do to look at the viable UV completions that are implied by this. And in general, it suggests that if you want to have light WIMPs, you really do also require a light mediator, like a dark photon.
Pat, can I just break in with a question at that point?
Mm-hmm.
So is there a way of seeing this point that you've just raised, that the LHC would probably be sensitive to the mediator, but you can't speak to that directly within the frame of the analysis? Is there a way of seeing that from the plot, or is there a health warning spat out by the code at this point, or is it down to the discernment of the user to recognize that that's what's going on?
It's covered in detail in the paper, but the code doesn't spit out a health warning here because, by using an EFT in the first place, you're presumably going to be sort of cognizant of this. The likelihood functions that you're using here are all sort of explicitly, take this into account. So if you're going to use these sorts of likelihood functions that turn off constraints based on the scale of new physics, presumably you have some clue of what that means.
Sure, no, but just to understand how this functions. It sort of requires the appropriate sophistication from the user to understand what's being said and what's not by the plot.
Yeah, it does for this sort of theory. One of the things that you have the option of doing within Gambit is actually putting in like parameter point warnings. I don't think from memory that we actually did that for this particular theory, but you can make it such that if there's something suspicious about a particular point that comes up, you actually log it. And then you can then basically go and plot distributions of suspicious points and, points that are suspicious in a particular way after the fact, that sort of thing.
No, okay, thanks. I'm just sort of interested in this question of, you know, where plots need to be read relative to the discussion section of their paper and when they can be taken out of context. And this is very much the first sort and not the second sort. Yeah. Cheers.
No worries. So yeah, there's also some interesting results for heavy WIMPs. So if you say that, so what I showed here was also using the relic density as an upper limit, right? So I'm allowing very low relic densities. If you demand a dark matter, this Dirac particle chi has to be all of dark matter, you get pushed up to very large dark matter masses. So the neat thing there is actually this leads to detectable signals at LZ. So here we've got the predicted number of events at LZ with this requirement that chi is all of dark matter. And you can actually see for, you know, just about all of the 95% preferred parameter space, you at least up to, you know, well, a few hundred GeV, you would get, you know, at least 0.1 predicted event in LZ, and in a lot of cases, you know, more than 10 events. So that's actually very promising, and it's actually kind of interesting theoretically, because this mostly happens to loop-induced operator mixing. So this is where you have a non-zero Q36 that actually mixes into Q16. So even if you have the Wilson coefficient for this Q16 0, you still get it generated via this operator mixing. And just to remind you, this Q16, this is the vector interaction, so the spin independent unsuppressed interaction. Now, of course, these sorts of operator mixing things can be screwed up if you actually include other effective operators that, you know, might mix in or cancel it and stuff like that. So, you know, we only had interactions with quarks and gluons, right? And we also had this flavored line set up, basically, where we didn't have separate Wilson coefficients for different flavors of quarks. So if you introduce new effective operators, this could change, right? So that's actually a fairly interesting avenue for future investigation. Okay, so I'll say something in about 4 or 5 minutes about this thing ColliderBit Solo. So ColliderBit has quite a large number of LHC analyses, and in fact, it's got the most of any similar tool. So by similar tool, I mean also MAT analysis and CheckMATE. But in order to access them, you actually have to put your model into Gambit, right? I've just told you about GUM, so it's not too arduous anymore. There's a relatively straightforward pathway for doing that. But very often we have people come to us and say, yeah, but I've got this random Monte Carlo sample I've generated. Why can't I just apply the ColliderBit constraints to that directly? I can't be bothered running Gambit. So we've listened to this, and what we're actually going to do is put out a new tool called ColliderBit Solo that allows you to use ColliderBit as a library. So it will take in a HepMC file, whether version 2 or version 3, generated by your favorite Monte Carlo event generator, and it will apply whichever of the ColliderBit LHC analyses you want to those Monte Carlo events. So it'll then spit out the likelihoods for those searches and also the relevant event numbers. So the predicted number will be the main thing you're interested in, but it'll also tell you the observed number and the background number from the analyses. It allows you to fiddle with all the options that you can normally fiddle with in ColliderBit. So you can combine likelihoods from different searches. You can choose whether to profile or marginalize over systematics. You can choose to use the best predicted signal region or choose to use covariances. You can choose different conversion settings, stuff like this. The input file for this ColliderBit Solo or CBS is quite simple. You basically list the analyses that you want to include. I don't know if you guys can see the top here. I kind of can't because of the Zoom thing, but it basically just says analyses, and then you list the analyses you want. And then you list the different settings. So these are the main settings that you would normally set when doing a Gambit run for ColliderBit. With a couple of additional ones, here you specify the name of the event file that you want to read in, for example. So at the moment, we're preparing a paper about CBS and also some other improvements in ColliderBit. And that's going to include a full performance comparison to Meta-Analysis 5 and CheckMATE, which is looking pretty good so far. So this is just one example. So this is for a Gluino search. This is the Atlas zero lepton search at 36 inverse femtobarn. And here what I'm plotting is the percentage difference between the predicted number of events for some cut flows. So cut flows that have been given by Atlas using the three different tools. So, getting bang on the actual Atlas cut flows is the gold standard. So you want to be as close as possible to this red line. So, and then down on the x-axis, I've got all of the different signal regions for this particular search listed. So you can see that CBS isn't doing better than the others in every signal region, but overall, it is doing pretty well, and at least by eye, it seems to be doing the best overall for this particular search. So I've told you basically about where we're up to with Gambit 2. Version 2 of the code is out. You can download it. You can use it. It includes GUM. So that means that you can do global fits directly from the Lagrangian, basically for the first time. We've also put out this dark matter effective field theory global fit. Has some interesting results for both light dark matter and heavy dark matter. And the code associated with that is actually going to come out as a small update as Gambit 2.1 very soon. And then just in the last couple of minutes, I told you about CBS, which basically allows you to apply ColliderBit analyses to external Monte Carlo without running Gambit. And we anticipate that should also be out sometime later this year. Thanks.
Great, thanks a lot. Do you have any questions for Pat? Ulrich? Okay, I thought Ulrich was going to ask a question because he hadn't muted himself. Maybe I can go ahead first. So, hello.
Now you can hear me. Sorry.
Hi.
Yeah, sorry. Increasingly many experimental papers will also, in the data they advertise, include various theoretical parameters inside them in their published data. So, for example, form factors, if you take something like B hadron decays. Do you have if they publish a full likelihood of that includes those parameters, are you able then from Gambit to link into that in some way and do an overall optimization?
Yeah, absolutely. So we're in the process of doing this. My student Chris Chang actually is doing this for the Atlas full likelihoods that are available at the moment. So the method is basically to hook up the codes associated with those, or put out by the experiments as backends. So like we call micromegas or Duxes or whatever, we call the likelihood code put out by the experiment.
Cool.
Can I have a quick question to Pat? But maybe I should know this, but maybe you can answer very quickly.
That's how all dangerous questions start.
no, it's just, look, when we are talking about the applicability of EFT, we're talking about the cutting off missing E. Is that somehow, well, I would have thought more generally that it should be kind of a momentum transfer or energy transfer. Is that?
Yeah.
somehow related?
Yeah, that's absolutely right. Strictly speaking, it should be momentum transfer, but to do that, you'd actually have to get in and do it at the event level when you're generating the events.
I see.
And the way we made this computationally feasible is that we actually generated all of the events beforehand and made a grid of collider yields and then interpolated on this grid. So in order to basically not have a prohibitively high dimensional grid that we had to pre-generate all of this stuff for, we made the approximation that, you know, we're going to use the missing ET as a proxy for the momentum transfer.
All right.
It's not perfect, but it was the best thing to do in the circumstances.
Okay.
Maybe I'll ask a sort of a question about the future. Is there any plan to look at for direct detection dark matter electron scattering? Because you got a lot of these constraints are kind of running into astrophysical bounds, and this could be quite a nice place to use Gambit, because you have various different constraints which aren't trivial to kind of interpret independently.
We have kicked around this idea a little bit. So what this requires is a modification of DD-Calc to basically, you know, I mean, the analyses in the experiments are different in the first place, right? So you need those likelihoods in there, but it also needs to be supported inside DarkBit. So Felix Kalhofer and Jonathan Cornell have been considering doing this, but I think the focus hasn't really moved to it in any sort of serious way yet. So it's kind of on the to-do list, but I guess it's not right up the top yet.
And to incorporate these direct detection constraints, are you kind of at the behest of the collaboration for them to provide you these likelihoods, or are there kind of approaches to do things maybe like approximately, maybe not fully robustly with the actual likelihood that the collaboration would use, but some kind of thing that captures maybe the typical signal?
These are all sort of approximate ones so far. There was some talk about getting a proper one from Lux at one point, but then that fell through, unfortunately. So I understand that LZ planned to release a full likelihood. So my information might be slightly out of date here, but I think that will actually end up being the first like proper full likelihood that we can get into DD-Calc. So yeah, everything else so far has been using what information is available in the papers, and then people like Felix basically making some sort of Herculean kind of guesses and then comparing the results that you get to what the different distributions look like, and then sort of tweaking things until they fit nicely.
Is that true for the various like indirect constraints as well, like these gamma ray constraints? Or
no, for the Fermi dwarfs, we've got the actual official public Fermi likelihood for that. In general, that's all we use. We don't actually use anything from like the galactic diffuse or the galactic center, because there's still debate about what's accurate to use there. So the dwarfs are really the most robust.
Yeah. Do we have any final questions before we close the official part? Don't see anyone. So